Davies. So Andrew Davies will be talking about strong lens detection using AI.
I'm in a really weird position in that a lot of the topics I was going to cover have been covered by previous talkers. So it's been really good, obviously, but you've sort of like stolen 4 minutes of talking from me. So, I'm fine with that, but yeah. Especially Jim's talk then, actually, it covers a lot of similar grounds. So I'm a PhD student at the Open University, and I've been trying to do strong gravitational lens detection with machine learning. So some of the topics to cover is, I'll just briefly explain gravitational lenses because, I'm familiar with them, but everyone might not be. Why we need AI and machine learning, which I think is obvious to most people in this talk. How we've used CNNs, quite a simple CNN for our classification model so far. Then I talk a bit about Gaussian mixture models and how we're trying to use these to deblend an image to separate into the source and lens components. And then I'll touch on what I'd like to do next. You may probably already know, but strong gravitational lenses occur when you've got a massive foreground object which causes light from a background source object to be lensed. And obviously they produce some really quite pretty images, as you can see from these here. When you've got an extended background source object, you'll get arcs of light. But if you've got a compact object, you'll get sort of multiple images, sort of the Einstein cross, some sort of quasar, background quasars, instead of these arcs of light around objects. So it's really quite advantageous to study these lenses because you can come up with some galaxy dark matter distribution models. You can detect objects that you wouldn't be able to see based on the observed magnitude because it gets magnified by the lens. And you can also constrain sort of Hubble parameters as well. So this is partly done because the Euclid Telescope, which is due to launch in 2022, I think is the current, I think that's accurate at the moment. So a lot of you may know more about the Euclid Telescope than I do, but so in its 6-year lifetime, it's going to, based on the ESA website, says it's going to observe 10 billion different sources over 15,000 square degrees of the sky. It will also have 3 Euclid deep fields, which cover about 40 square degrees of the sky. There's a bit more information about it there. So 10 billion sources is great, but strong lenses are rare objects. So with the Euclid Telescope launching and LSST as well, we expect to, have we got it here? Yeah, so 10 to the 5 strong gravitational galaxy-galaxy lensings may be observable based on this data. Now, 10 to the 5 is a huge number, but it's not big compared to 10 billion sources. So sort of 1 in 10 to the 5 may be lensed, and that's obviously not going to be achievable by current methods of visual inspection. So this is the big push for machine learning methods. There's been sort of citizen science approaches which are more scalable than obviously individual doing visual inspection, but if we can have a good computerized model that we can just throw computer power at, that's obviously a lot more scalable than even citizen science approaches, provided we have a good method of doing this. So a couple of years ago, there was a strong lensing finding challenge in the Euclid Consortium where they produced a lot of simulations in order to create a data set large enough that we could train machine learning models on. 20,000 images were released by them for us to train our models on, and the challenge was to classify 100,000 unseen images in 48 hours. And the 48 hours is only there as a restriction to show that the models can be done very quickly and that you can't have time to visually inspect them all. Although one team did visually inspect most of the images in the challenge and got, I think, about 75% accuracy. So it's a very good accuracy, but they were beaten by machines. And it was a lot less effort for the machines to do it than the humans. There were 2 different types of data sets produced. Ones were sort of Euclid-like, and the others were kids-like. So I say Euclid or kids-like. There weren't exact representations of what we're going to expect from them, but they have similar noise levels, similar pixel scales, and have similar sensitivities. So they're meant to be a good representation of what the images we expect to get from Euclid and the kids-like images. The Euclid-like images have only a single band, and the kids-like have 4 image bands. I think I've got examples of some next. So this is how they've simulated the images. They've taken, on the left, a real galaxy image with no lensing. It's just a single galaxy there. They've simulated a lens, as you can see in the middle, and then sort of added the two together, whilst keeping noise levels and pixel scales the same to be representative of Euclid or kids. Got examples here of when you have 4 image bands. These are sort of what the simulations look like. So you can see this is a really good obvious example. I don't know how obvious it is on that screen, but this is one which would be easy recognizable by eye. A human would have no problem saying this is a lensed image, but that's not obviously the case for computer models. So here are some false color images based on some of the images in the simulations, just so you get a feel of that. They're not all obvious Einstein rings, and not all have obvious nice arcs. Like the image in the middle is lens. It's difficult. Oh, it's actually much nicer to see up there. Actually, that's quite nice. But certain images, for example, this one has absolutely no lensing in. But we need to be able to obviously call these from the data set so that we can say there's no lensing as well. And then you get, if you look at the last but one image here, this isn't a lens, it's just it's a problem. It's a problem because our computers say it could be a lens. When it isn't a lens, it's just something else, basically. We don't know, based on the simulation. So we took a CNN approach to this because of how good it is at image classification in sort of more day-to-day issues. As you can see, this is the Sci-Fi 10 data set where they have, I think, maybe 10 million images or 100 million images of everyday objects with 10 different classes. And current CNN methods have about 96% accuracy at recognizing what class each image falls into. So this is a very good image classification tool. However, the lenses aren't quite sort of everyday objects as easy to recognize as these, possibly. CNNs also are very good at the handwriting recognition, sort of with the MNIST 60,000 data set. They've done, as well as humans can do, in some cases, sort of a bit better, because some of the digits they can't classify are ones that actually, if you looked at yourself as a human, you can't classify either because it's just a squiggle. You've got no idea what it could be. So yeah, so they're a good tool to try. There's also this paper, I think early 2016, which was using CNNs to classify between stars and galaxies and astronomical images. So they've taken the advantage of CNNs in everyday images and said, let's apply it to this data set, and it's worked really well. I think the area under the ROC curve was about 0.96 for, 0.99 for this problem, and they had a galaxy completeness set of 0.96. So they managed to get 96% of the galaxies back as confirmed as galaxies. So it's a really nice result. So this is our really, really quite basic CNN here, and you wouldn't even call this deep because of how many few layers there are. The interesting thing to me is CNN is something I didn't do before, so this is all sort of new to me before trying to do this image classification challenge. So this one has 4 convolutional layers and just 2 fully connected dense layers. I won't go into this at all. There's more information if you want it, but it's basically a very small network. It's only 4 convolutional layers and 2 dense networks. Now I wanted to sort of show going into the delving into the black box of CNNs and try and show what some of the image kernels look like. Unfortunately, our convolutional layers, the kernels are only 15 by 15 pixels. And when you blow it up to that sort of size, it sort of becomes a bit nonsense. But if the images weren't that big, you can see a lot more features than you can see on these, for example. So if you look at the far left one over there, it's interesting that the colour information is really quite key here. So this looks like a traditional edge-finding kernel where you've got black and white down the middle. But because because we have 4 image bands, it's not black and white, we have a separation between sort of bluey green colours and red colours. So it's looking for an edge in different colours across the bands. And same with this one here, we've got the green and the blue on this side. These two really aren't clear on the screen at all, so I'm really sorry about that. But when you look at it on a much smaller screen, you can see here there's a vague green area here around the centre of the shape, which is sort of looking for more curved, darker, redder features rather than the green feature in the middle, to try and recognise these arcs, is what we think it's trying to do. But they are a bit of a black box, but this is the best way I could try and work out what it was trying to look for. I'll just, this is the results in a slide, in a poor table. But you can see the big advantage of having multi-band data compared to single-band data. The accuracy shoots up, and not only the accuracy, but also how many lenses you get correct, which is the more important factor, really, based on how rare they are. There's a first-year PhD student who's taken similar work to what I've done, and he's modified it and made his own classifier based on some of the work I've done. He's made some extra simulations where they are compound lenses. So instead of just one object being lensed, there are now 2 objects being lensed, including the lens being lensed. So they can create a big subset of what the image is going to look like. So it's not just one arc, it's multiple arcs at multiple radii with multiple length of arcs as well. So I think on his preliminary work, he's got about 80% accuracy across the board. So this is important to note because in the Euclid data set, we won't get only single lensed images, we'll also get some of these compound lenses. So it's really good to know that these can be picked up in the same networks as well. So it's not an issue having compound lens, we still detect these compound lenses. And that's the work Josh has been doing. So this is going on to a sort of similar scope to what Jim was just talking about as well. So some of the work I'm trying to do as well is to sort of deblend the lens. So we've got the simulations, and we want to say, yes, we've got this image, can we deblend it to 2 different sources? A background source and a lens source. Now that's easy when you've got a really nice image such as this. And the main advantage here is any false positives you get from your convolutional neural network, you can then apply this to, and it can tell you if it's found 2 sources or just 1 image source. So that is hopefully a method of culling out a load of those false positives and having a pure sample from the output of the CNN. So this is done, this is a bit more explanation. That actually, dividing the pixels is a lot easier than dividing the pixel flux in the image. So instead of saying this pixel belongs to this image, this pixel belongs to that image, you want to divide that pixel and say, this part of the flux from this pixel belongs to this image, this part of the flux belongs to that image. Which is obviously harder than doing it just by pixels. So this is just a sort of a stock image from the scikit-learn method of using Gaussian mixed models. It's a probabilistic method which tries to fit Gaussians to data, and the Gaussians have unknown parameters, but it tries to fit them as best it can. It's got a more advantage than k-means clusterings because it takes in the covariance of the data as well, so that you can have a greater scope of Gaussian shapes, and it uses the expectation maximization algorithm to fit these to the data. Now, this is an example of a nice false color with 4 different image bands here. So what we try and do at the moment is we say, let's compare 2 of the image bands. So here on the x-axis we'll have 1 flux band, here on the y-axis we'll have 2 flux bands. And as you can see in this really obvious example, it's really obvious that there are 2 distributions here. There are 2 sets of data points there. And if we apply it to this simple 2D case, you see the Gaussians fitted are plotted here in red and black. And that gives an okay separation. It's not great, but it's okay for sort of a proof of concept proxy little model. But instead of just doing it in 2 image bands in 2D, we can do it in 4D, which gives a much clearer separation between 2 objects. And here we probably apply a threshold and say, actually, anything below 0.5, let's not plot. So that here you probably have 2 distinct objects. now I can't show you the plot in 4D, obviously, but what we do here is we have 4D data points, and we try and plot 4D Gaussians to come up with a better model than just the 2D case. Some of the feature work I'd like to do, if time permitting, is to, for the CNNs, come up with several different models and come up with a way to join them all at the end. So different models are sort of like a different person's opinion looking at an image. So each one will have a slightly different opinion, but together, applying some logic, you can come up with a more pure result. And at the moment, using the Gaussian mixed models, because we have simulations, we actually know which pixel belongs to which part of the image, so we can work out the fluxes. So we've done it all unsupervised so far, but there's scope to do it with the supervised learning and fit across all the lenses that we have and try and have a better output by using supervised learning. I think that's it.
Slightly naive question, perhaps, but if I understand you correctly, all your training is done on simulations.
Yes.
So, with a real sample where humans have actually labeled information, I mean, how reliable is it to translate what you've done on simulations to real data?
Once we trained this model, we applied it to actually the lenses in the cosmos. And so I think there's 65 lenses in that sample with a slightly different pixel scale. So we applied kernels to try and modify it to be as representation of Euclid as possible. And it returned most of the lenses that we could identify by eye. So it said, I think, about 70% of them were lenses in a 100% lens sample. And by eye, you can't recognize all 100 anyway, all 65, sorry. So it was really quite good. It was almost on par with humans, based on that small 65 lens sample.
Okay, but does that scale to data like Euclid or LSST?
I haven't tried on the Euclid set. So the team that did the Euclid classification by eye, it'd be really interesting to see where we differ. You know. But yeah.
Hello. Yes. Interesting talk. So you showed showed the architecture you came up with for your convolutional neural network. What was the process that you went through in order to decide on that architecture? I mean, are you using? I didn't see the full network, but are you using different kernel sizes to try and bring out different features?
Yeah. So it was actually based on some work by Petrillo in 2017. I was sort of playing around with making the model myself and things, and had a similar sort of thing, but then built on what he did in his paper. So it's a similar model to what he's got, and it differs because I was trying to work out what the image kernels were doing. So the first two image kernel layers have a sort of 15 by 15 size, which is quite a large kernel size, especially considering the images we have are 101 by 101. So it covers a significant portion of the image. So there wasn't any particular reason for using large kernels, more that just I was interested to see how it would learn, if it would come up with these traditional edge detection methods.
So when you say about doing, maybe in future doing ensemble models, is there some kind of systematic way you've come up with of or thinking about in terms of being able to pick out architectures which optimize this problem?
Possibly, yeah. So maybe playing around with different models having different kernel sizes, try and pick out different scales of features might be a really good method to try and get. Yeah, good point.
So you showed a plot showing the CNN where you delved into it.
Right, yeah, some of the image kernels. Yeah.
I was wondering how you made that. Did you take a particular layer of convolutional network and plot the weights there, or?
Yeah, so what the convolutional layer does, it comes up with image kernels and it trains and it comes up with these sort of values between 0 and 1. And then because we have 4 image bands, it creates a kernel per image band. So it comes up with 4 different arrays, basically, and we false color these to see how it... so darker colors here, which are... the darker colors have a higher weighting in the image. So when you apply that kernel to parts of the image, the darker parts will have a higher carry forward through to the later layers, if you like.
You didn't just pick a particular layer, you took it from averaged across all
Oh, I see your point now. No, so yeah, so this is the first convolutional layer. These images are from that. Looking at the later ones, the 5 by 5 pixels, it's a lot more difficult to see structure. So that's why these are shown and not the other ones, for example. So.
Hi there. Here I got a little bit suggestion that there is something called activation map.
Action version mapping, you say?
Yeah.
Okay.
So actually use that technique, you can get the Python code from library. Then you can see what's going on inside the convolutional network. Then it can show where this convolutional architecture focus on in this activation map. So you can try it out.
Okay, that's really interesting, because actually some of the work I've done sort of, not related to the PhD and things, is using deconvolutional things to sort of map the areas where it lights up, where the kernel found more interesting parts. So the parts of the image which were more weight-heavy based on the decision. So if it said it was lens, these are the parts of the image where it made that classification based on. So it sounds like a similar thing, but yeah, I'll check that out. Thank you.